Hello everyone, in the lecture today we will try to finish all the rest topics in the highway subgrid structure design. First, let's have a quick review about the pavement structure, which is usually applied with the layered system. In our previous lecture, we have learned the subgrid layer, which is constructed with the in-situ soil. The layer is very sensitive to moisture contents, and the strength of the layer is relatively small. About the subgrid layer, there are base and subbase layers. Both of them have free draining capability. Usually, the strength of the base layer is much larger than the subbase layer. Both base and subbase layer are constructed to support the load applied to the asphalt surface. In this lecture, we will focus on introducing the property of base and subbase layers and the materials applied for them. Both base and subbase layers are actually granule-based cores. In general, the granule-based course is introduced to support the working load, and it will be used as a drainage layer to remove the water behind the pavement. Also, it could be applied to prevent the first heave effect. To achieve this goal, usually the granule-based course will have some specific properties, including high internal friction angle, high permeability, and low contents of fines. For the design of the granule-based course, we should follow the guidelines provided by OPSS, Ontario Provincial Standard Specifications, or AASHTO. In OPSS 1010, the granule A, B, and M are selected as the materials for granule-based course. The base course can be constructed with both unbound granule aggregates and bound materials. The unbound granule aggregates can be some new aggregates such as crushed rock and gravels. They can also be recycled materials, including recycled asphalt pavement (RAP) or reclaimed bituminous materials (RBM), and recycled aggregate concrete (RAC). Some other materials, such as blast furnace slag, can also be the unbound granular aggregates. The table here shows the requirements of the gradation for granule materials defined in OPSS 1010. Basically, for the pavement design, we want the strength and drainage properties for the granule materials. In addition, we can control the strength and drainage of granule materials by controlling the gradation. Usually, granule A and granule B may have the same gradation, but the physical properties of the particles might be very different. If the material with the granule A gradation but a poor physical property, it will usually be defined as the granule B material. The figure here shows the percentage passing range of granule A and granule B materials. Basically, we can see that the range of granule A material is fully covered by granule B material. This indicates that for some granule B material, their gradation will be the same to granule A material. In that situation, we need to double check the physical properties to classify the materials. The table also lists that Los Angeles abrasion loss is one important factor for the selection of the base course materials. Usually this loss is determined by the Los Angeles abrasion test, which is defined in AASHTO test 96. The figures in this page shows the instruments applied for the test. Basically, the Los Angeles abrasion test is applied to produce the abrasive action. It will use some standard steel balls and mix them with aggregates. Then they will be placed in a drum and rotated for a specific number of revolutions. The figure on the right bottom shows the status of the aggregates before and after the test. You can see that the aggregate was crushed to smaller pieces. There are some typical Los Angeles abrasion loss values for different aggregates. Basically, the L.A.ABRASION loss value is defined as the percentage changes of the aggregate mass before and after the test. The equation here shows how to calculate the loss value. Basically, the mass before and after the test are all weighted as the particles retained on number 12 sieve with the grain size higher than 1.7 mm. The table on the left shows the typical loss values for different rock types. In general, for hard igneous rock, the loss value is around 10, and for soft limestones and sandstones, the value is as high as 60. And at the bottom of the table, we also can see the ranges of the loss values for some specific rocks. Micro-DeWalt test is another abrasion test to measure the aggregate toughness and abrasion resistance. Different from the L.A.ABRASION test, the micro-DeWalt test will use much smaller drum and smaller steel balls. In general, the micro-DeWalt test is applied to polish the aggregate particles, while the L.A.ABRASION test will try to break these particles. OBSS also introduced more laboratory tests to evaluate the physical properties and set up the physical requirements for base course materials. From our previous lectures, we also know that freeze-thaw effect plays an important role in the pavement performance, and they are actually one of the major causes of the pavement distress. In order to understand the freeze-thaw loss in the pavement design, we need to introduce the sulfate soundness test. The test procedure is defined in AASHTO test 104. This test will simulate the freeze-thaw effect with the crystallization. In the test, we will first oven dry the sample and separate it into specific sieve sizes, and then the weight of the materials with respect to different sizes will be measured. Then the sample is immersed in a saturated solution of sodium or magnesium sulfate, and let it remain at a constant temperature for 18 hours. And then we will remove the sample from the solution and dry it to a constant weight and a constant temperature, 110 plus minus 5 degrees. We will then repeat this cycle for 5 times, and then wash the sample to remove the salt and dry the sample. After that, we can determine the loss in weight for each specific sieve size, and then compute the weighted average percentage loss for the entire sample. The two figures here shows the aggregate particles before and after the test. By comparing these two figures, you can see that there are more smaller particles after the test, and you will also see some cracks showed on the aggregate particles. Another thing I want to introduce in the lecture today is bond-based materials. Usually these materials are introduced to improve the strength and reduce moisture susceptibility of soils. In general, there are two types of the methods to construct the bond-based materials. The first one is a bitumen-treated base course. In this method, we will add a 4 to 10% cutback or emulsion to soil, and the soil should stay at the optimal moisture content. After that, we will compact the soil to a designed compaction level. In this method, the amount of the binder added to the soil is determined by the amount of the fine contents in the soil. The second method is the cement stabilization. In this method, we will add 3 to 16% of Portland or slag cement into the base course. Sometimes we will also apply the fly ash and lime to the base course. For the preparation of bond-based materials, we see that if the material is substandard and you want to improve the performance of the material to support the pavement, you can use the cutback asphalt, emulsion asphalt, or cement. Here, emulsion means that you will put the asphalt with water and emulsifying agent. The cutback means the process of adding the asphalt with volatile petroleum solvent, such as gasoline. With that, the asphalt will be dissolved in the solvents such as kerosene, gasoline, and diesel. The reclaimed materials are also commonly applied for base course design. One of the most common reclaimed materials is reclaimed asphalt pavement. When the asphalt pavement is pulverized up to 50%, then it could be used to replace the mineral aggregates. The second type is steel slags. This one is very similar to aggregates, but usually it will have some pores and rust on the surface. With these features, the steel slag is very sensitive to water and it can expand with moisture. Sometimes you will observe many unexpected changes about the components with the presence of the water. The last one would be the reclaimed glass or ceramics. They can also be used as the reclaimed materials for the base course. The figure here demonstrates the gradation of reclaimed bituminous materials, which is just the reclaimed asphalt pavement. In the figure, we can see the solid lines, which are the gradation of the RAP RPM. They are all within the limits of the granular A materials. It indicates that the gradation of the RAP and the RPM will be very similar to granular A materials. And hence they will have very similar strength and drainage properties, so that we are able to mix these two types of materials together for the base course design. The figures here demonstrate how to construct base course with reclaimed bituminous materials. At first, we will pulverize the asphalt concrete pavement and then mix the RPM with the granular base. And finally, we do the compaction about the materials for the pavement. In general, we will set the portion of the RPM in the base course as 30% to reach the optimal performance of the pavement. There are a lot of advantages of using reclaimed materials in the base course design. The most significant benefit is the low cost of the pavement, especially reductions in materials and labor cost. However, the drawback of these materials is also obvious, as the quality of the reclaimed materials is lower than the original material. It will not be as durable as the original asphalt. In that sense, it will cause more cracks and potholes on the surface. The figure here shows the pavement with 30% RAP after 10 years, and you will actually observe a lot of cracks along the pavement surface. Here are two other examples about the pavement with reclaimed materials. On the left, you can see a clear longitudinal joint crack. On the right, there will be a lot of alligator cracks happening at the edges of the lane. There are some critical issues we need to take care of when using the reclaimed materials for pavement design. Actually, the contents of the reclaimed materials has very significant impact to the soil properties. From the two figures on the top, we can find the relationship between the CBR and the RAP contents. We see that by increasing the contents of RAP, the CBR values can be reduced dramatically, which means that the strength of the soil will become much smaller. However, if you check the two figures at the bottom, where it shows the relationship between MPR and the different RAP contents, you can see that by increasing the RAP contents, the resilient modulus will be larger. However, the changes is not that significant as the CBR values. In this page, the figure demonstrates the relationship between the accumulative strain, which is applied to measure the deformation and the rotting of the pavement, with respect to the number of load repetitions. Each line in this figure shows one contents of the reclaimed materials. We can see that by increasing the contents of RAP, the accumulative strain will be larger. That indicates that there will be larger distress happens to the pavement. So in reality, when we are trying to use the reclaimed materials, we have to make sure that the content of RAP should not be larger than 50%. And actually, usually we will choose 20 to 30% to achieve the optimal performance of the pavement. Another reclaimed material is roller compacted concrete, RCC. RCC is actually a zero-slumped Portland cement concrete with a very low water-cement ratio. This one was developed in the 1980s. When RCC is used in the flexible pavement design, it was usually placed with an asphalt concrete paving machine and compacted with a vibratory and rubber-tied roller. In that sense, the flexible pavement becomes semi-rigid granular base or composite pavement. Usually, the fatigue resistance of RCC is very low, so it can easily generate cracks along the pavement. The experience of using RCC in Ontario is not very good. We observe cracks everywhere along the pavement. This figure shows how we use RCC for the pavement. We will have zero slammed PCC with a very low water-cement ratio, and then you mix it with the asphalt and it's compacted on the road for the pavement. In pavement design, sometimes lean concrete or ECONOCRETE based subbase layers will be proposed to provide a uniform surface to the pavement structure or to prevent the direct contact of the pavement to the ground soil. The lean concrete is actually the mixture of the cement and water, where the amount of the cement is lower than the amount of the liquid. The page here lists one typical amount of the components in the lean concrete. For the cement content is set as 133 to 178 kg per meter cube, which is approximately 7%. The slump is 25 to 75 mm. Air content is 3 to 9%. The compressive strength is actually very small. It's set as 5 to 10 megapascal. There will be a lot of advantage of using the lean concrete base subbase. First, this kind of base will have very high strength and high stiffness. In that sense, it's able to provide strong support to the upper layers. Also, it's in a thinner section so that the pavement depth won't be very high. Also, the concrete is not erodible, so it can last for a longer time. And this one can provide some improved load transfer from top to the bottom. However, this kind of base subbase structure is not recommended for the flexible pavement structures. As you may know that for the flexible pavement, the distribution of the load will usually be concentrated. In that sense, it will easily cause the cracks or distress to the lean concrete layer, which will cause some failure of the pavement structures. Another type of the pavement base is open-grade drainage layer, which is also called the asphalt treated permeable base, ATPB. ATPB is usually used as the drainage layer below the dense graded hot mix asphalt, stone mix asphalt, or PCC slabs. This layer is designed to allow water passing through as quickly as possible. With this layer, we can prevent the collections of the water under the pavement. Usually, this layer will use the open graded mix with the AC contents of 1.8%. It will be very different from another course, open graded friction course, which will also use the open graded mix. The open graded friction course will have a much higher stringency specification than ATPB. For OGFC, different from the normal asphalt concrete with the AC contents of 4 to 5% and air voids of 4%, the OGFC will usually have the air voids around 15%, and this value can be even higher as there isn't any upper bound about the air voids percentage. So that's all about the lecture today. With that, we finished all the topics in highway base, subbase, subgrade structure. Thank you very much for your attention, and I will see you next week.